Hi, Assalamualaikum everyone. For this video number 2 for Fourier transform chapter 3, which is part 2. So for this part, I'm going to explain on the Fourier transform properties and show you some examples. And these are the properties of Fourier transform, okay, from linearity and superposition, time shifting, time scaling, which we already learned about this in times domain, and then the duality, the frequency shift or modulation, convolution, and also differentiation. Okay, the first properties here is linearity and superposition. So if there is a time domain signal given as V1 and the pairs of this time domain signal is given as capital V1 omega, and we have another signal which is V2t, and the pairs of Fourier transform which is in frequency domain is V2 omega, and if there is another numbers here, or A multiplied by V1t plus BV2t, okay, and this is also equivalent when we perform the Fourier transform, and this is equivalent to A V1 omega, okay, in which the same A we multiply by the Fourier transform for V1t plus B V2 omega. Okay, so this is the linearity and superposition properties. Okay, the first example here shows you how to use this linearity and superposition properties to find the Fourier transform for signal given as 3 exponent negative 2 magnitude t here. Okay, so the solution here, we obtain 3 exponent negative 2t here. We open up the equation. This is basically equal to 3 exponent negative 2 tut plus exponent 2tu negative t. Okay, from table C2, we find out that for exponent negative 2 tut, the pair of Fourier transform is 1 divided by 2 plus j omega. And another one here, if the t here is negative, okay, and the omega here should be negative as well. Okay, using this answer here, we put together because this is the linearity and superposition properties. So it means that the Fourier transform for these two functions can also be added up together like this. Okay, this is in time domain, so we add together in frequency domain. Okay, we add 1 divided by 2 j omega plus 1 divided by 2 negative j omega and multiply back by 3. Okay, and we solve for this, we will get 12 divided by 4 plus omega squared. Okay, and this is the time domain for this function, 3 exponent negative 2t, and this is the Fourier transform plot, okay, for this function f omega. And there's another example here using linearity and superposition. For this example, you need to find the Fourier transform for the given signal as shown below. So if we refer back to the table, we couldn't find the same exact signal as given for GT. What we can find is actually the rectangular signal. So for the original rectangular signal, we know that for time domain signal, which is A rectangular T over tau. Okay, so you refer this to the list of table. The drawing here is this is A, this is negative tau over 2, tau over 2. So it means that here the signal have this graph here have signals from negative tau over 2 to tau over 2. The duration here is tau. Okay, so from here we can match back to this signal. We know that signal GT can be produced by using the superposition between two signals. In other words, if we add these two signals, G1t and G2t, okay, from negative t to 3, we will get this shape. Okay, so if we check back here, from negative 3 to negative 1, there is no signal at G2t. So basically, we add 0.5 by 0. So this is 0.5. From negative 1 to 1, here is 0.5 and here is 1. So 1 plus 0.5 is 1.5. So we added these two signals, we can get this. So we want to find the Fourier transform. Okay, we have to break the signals into two rectangular signals. Okay, from this, we need to find out the original equation in the time domain. So from here, we can see that the tau given here is 6, and for this one is 2. So from here we know that the A here, okay, which is the amplitude here, is 0.5 and this is 1. So for the first G1t here, this is 0.5 rectangle t over 6, and for the second G2t here, this is rectangle t over 2. Okay, so from here we can use the Fourier transform pairs for the rectangle signal. And then based on this, refer to the table, A rectangle t over tau, and the Fourier transform here is given as A tau sin omega tau over 2. Okay, so this should be the pairs. Okay, so we mesh with this signal here. For the first signal here, okay, the tau here, the A here is given as 0.5 and the tau here is 6. Okay, so just put in this equation, okay, 0.5 tau sin, tau here is 6, and omega divided by 2, and solve it, we will get 3 sin 3 omega. And for the second one here, tau here is 2, A here is 1. Okay, so multiply A and tau, become 2 sin 2 omega divided by 2, and solve it, 2 sin omega, it becomes 2 sin omega. Because GT here is G1t plus G2t, so we know that the superposition and linearity properties of the Fourier transform is the capital G omega here is equivalent to G1 omega plus G2 omega. So we add the answer that we obtained for the Fourier transform for G1t and also G2t. So this is the final answer, 3 sin 3 omega plus 2 sin omega. Okay, and the next properties here is time shifting. Time shifting, time delay of a signal causes a linear phase shift in the spectrum of the signal. In other words, when for the time domain, if there is any time delay of the signal in the frequency domain, it will cause a linear phase shift. Okay, so if the signal is delayed by t naught, the phase spectrum will also be shifted by negative omega t naught, and there will be no change in the magnitude spectrum. The equation here, if Vt, the pair or the Fourier transform for Vt is b omega, so when there is delay here or the time shift here by t naught, so for the Fourier transform it becomes v omega exponent negative j omega t naught, right? Okay, now we want to see some examples, and the first one, find the Fourier transform for signal 3 exponent negative 2 t minus 0.5. Okay, basically this signal is a signal of 3 exponent negative 2t, which we have solved before, and this has been shifted by 0.5 second. And from the table, actually, previously we solved it using linearity and superposition, but there is a solution from the table, which is given as exponent a exponent negative at here, and the pair of the Fourier transform is given like this. Is given like this, and when the signal is shifted by 0.5, okay, and put in the value, we will get 12 divided by 4 plus omega squared exponent negative j omega over 2. Okay, this has similar magnitude with example 1, but however we have a phase shift by 0.5 omega, okay, which is omega divided by 2. Okay, so when we plot this signal in terms of time domain, it is shifted. Okay, it is shifted by 0.5. So this is the frequency domain, okay, of Fourier transform of the signal, which has the similar magnitude as the example 1. However, the shift here has been shifted by negative omega over 2. Okay. Another example is to find the Fourier transform for this pulse signal. This is actually a rectangular signal which has been time shifted by tau over 2 to the right. Okay, so the Fourier transform for this signal is given as this. Okay, how I obtain this? Remember that the Fourier transform or for the rectangle signal is given as a tau sin omega tau over 2. To obtain this formula from the table, and then because this is shifted by tau over 2, and we have to multiply by exponent negative j omega tau over 2. Basically, this is a similar magnitude with signal A rectangular t over tau, but we have phase shift of negative omega tau over 2. So when we plot the signal in terms of the magnitude, this is the sinc function on the positive side with the same amplitude, which is A tau, and the phase here is shifted by negative omega tau over 2. The third property here is time scaling. Okay, so time scaling is given as VAT, where A is any real constant. So the pair for the Fourier transform for the time scaling properties is given as 1 over A V omega divided by A. So if A bigger than 1, so this you need to recall back your knowledge in the first chapter. If A bigger than 1, the signal Vt will be compressed, but this will produce expansion in frequency domain. So this is the opposite effect. Or else, if A small letter a here is less than 1, the signal in the time domain will be expanded, but for the frequency domain it will be compressed. Okay, so again it has an opposite effect. Okay, so example here, if given Vt as rectangular function and V omega here we obtain from the table, which is A tau sinc omega tau over 2. So if V1t here has 2 as a constant, okay, in the bracket here, and we put in the formula here, okay, so this is a rectangle, okay, 2t over tau. And we put in the formula, V1 omega will become, basically 2 here is A, so you put 1 over A, which is 1 over 2, V omega over 2, omega over 2. So this omega over 2, you replace with this omega. Okay, with this omega. So here, you also have A tau. So A tau over 2. Sinc, when you replace this omega with omega over 2. Okay, so replace this with omega over 2. So basically, it will become omega tau divided by 4. Okay, so this is how you want to solve the time scaling property. Okay, if we see the plotting, for this, the original signal here is given as a rectangular function, and this is the Fourier transform for the rectangular function, which is a sinc signal. And if the signal here is compressed, the Fourier transform for this signal will become expanded. Okay, will be expanded. Alright. Now we move to another properties, which is duality. For the duality, if given the signal Vt and the Fourier transform is big V, okay, capital V omega, so if we found any time domain signal with the same shape as this V omega, but somehow in time domain signal, the pair here is 2 pi V negative omega. Okay, in other words, the duality of a signal means that frequency spectrum for Vt will have the same form as time domain signal Vt, but having inverse operation of frequency and amplitude scaling of 2 pi. And this is useful to obtain Fourier transform for time domain signal which have the same form as non-frequency form. Okay, for example here, if we have we have a time domain signal which is rectangular signal, and the Fourier transform pair here is a sinc function. Okay, and if we want to find the Fourier transform for the sinc function in time domain, basically the Fourier transform will be in terms of rectangular function, okay, which is the opposite. That is why we call it duality. However, this has the inverse operation of frequency, okay, which is negative omega, and also an amplitude scaling by 2 pi. Okay, let's see some example to make more sense. Okay, in this example, find the Fourier transform for signal gt equal to A tau sinc t tau over 2. So this is familiar, right? But somehow we've seen this before in terms of Fourier transform or frequency domain, which is in omega. So for now, the solution here, we know that the pair of these should be in terms of rectangular function. Okay, because when we refer to the table, we know that A rectangular T over tau will give the Fourier transform in terms of sinc function, which is A tau sinc omega tau over 2. So for the duality properties, okay, we mesh this, okay, A tau sinc T tau over 2. Okay, this is in time domain, not omega. Okay, if you see here, this is the Fourier transform. However, this is in time domain. So because of that, we can take the rectangular function as the Fourier transform for the sinc function. However, this is in terms of negative omega, meaning that we replace t here with negative omega and we multiply by 2 pi. Okay, so this is in terms of the plot. If we have Vt as the rectangular signal, the Fourier transform is sinc function. However, when we want to find the Fourier transform for the sinc function in time domain, okay, which has the same magnitude A tau, okay, as the Fourier transform for the time domain function, we know that the Fourier transform must be in terms of rectangular function. However, we have the scale, amplitude scaling by 2 pi, so this will become taller than the original rectangular signal. Okay, and basically we have negative omega, which has the negative effect of the phase. But since the rectangular signal is basically the symmetry signal, this does not give any effect, okay, to this example, for the rectangular example. Okay, and then the next example here is a frequency shifting or modulation. Okay, given that Vt is Vt and the Fourier transform of Vt is V omega, so frequency shifting happens if this Vt or time domain function multiplied by exponent negative j omega naught t, or multiplied by cos omega naught t, or multiplied by sine omega naught t. This we call it frequency shifting, or in other words modulation. So if you see frequency shifting or if you see modulation, you know that you can use this formula. Okay, we will learn more about this in the Fourier transform application. Okay, so remember that any signals multiplied by exponent negative j omega naught t, which has omega, okay, which the signal must have this omega, okay, which refer to the frequency, or multiplied by cosine or also sine signal. We will know straight away that this is frequency shifting or modulation. So when this time domain signal multiplied by exponent negative j omega naught t, the Fourier transform will become V the omega minus omega naught. Okay, so just put in the value. Okay, if the Vt here is multiplied by cosine function, it will become like this. And if it multiplied by sine function, you need to divide by 2j, and this one will become minus. Okay, and if you see at the example 6 here, we need to find the Fourier transform for signal dt ft cos 20t, where ft here is given as 2 rectangular t. Okay, so basically you need to know how to plot the rectangular t. So rectangular t, here this is a rectangular t, and it has 2. Okay, it has 2 as the amplitude. Okay, basically this is the rectangular t. Okay, the shape of the rectangular t. When multiplied by the cos 20t, so it becomes something like this. Okay, so first we want to find the Fourier transform for the ft here. So given ft here as 2 rectangular t, we put the value which we found from the table. Okay, so the table gives you that the Fourier transform for the rectangular signal is A tau sinc omega tau over 2. Okay, this is sinc. Okay, now you put in the formula. Okay, will become 2 sinc omega over 2. So we know that for the these properties, which is the modulation, okay, we refer back to the formula where Vt multiplied by cos omega naught t, we have to put 1 over 2 V omega minus omega naught plus V omega plus omega naught. Okay, we have to minus the omega naught and plus the omega naught. Okay, so for this example, the omega naught here is 20. Okay, this is the omega naught. Okay, and we already obtained f omega. So basically what we have to do is we change this omega, okay, in f omega into omega minus 20 and omega plus 20. So to put in the form of the Fourier transform for g omega, this is equal to 1 over 2 in case square bracket f omega minus 20 plus f omega plus 20. Okay, so in other words, you have to find the Fourier transform for ft, so which we already obtained here, 2 sin omega over 2. So you put 2 sin, however, omega here you replace with omega minus 20 because 20 here is omega naught, alright, and then divide by 2 plus 2 sin omega plus 20 divided by 2. Okay, so for this we will get sin omega minus 20 over 2 plus sin omega plus 20 over 2. Okay, so basically when you want to plot this g omega, okay, this is a sin omega minus 20, okay, which is at the positive side, and this is basically a negative. Okay, this is actually negative. Plus sin omega plus 20 divided by 2. Okay, so this is how you plot the graph. So basically we can see that for the modulation, okay, the signals here have been divided into two parts, which is the negative part and also the negative part here and also the positive part. Okay, so the next properties here is convolution. So I hope you have already watched the convolution part for the time domain signal. Okay, this is crucial because your MATLAB assignment will involve this convolution in terms of time domain and also in terms of the frequency domain. So for the frequency domain, the convolution process is much more easier compared to in the time domain. Okay, so in order for us to perform the convolution, okay, we need to understand the interaction between the input signal and also the impulse response, okay, in the time domain. So given the linear time invariant system with the impulse response ht and the input signal xt and the output signal yt, convolution is the interaction between the input signal xt and also impulse response. Okay, in terms of the time domain, this one is xt convolved by ht. So the output for any input signal can be obtained from the integration between input signals and the system impulse response. This is in terms of the time domain. xt convolved, the symbol here is convolved by ht. So this is the integration of negative infinity to infinity x tau h tau minus t d tau. So I hope you have already understand the convolution in terms of time domain. However, for the frequency domain, it is much more easier because when you convolve V1t and V2t, given that V1t has V1 omega as the Fourier transform and V2t has V2 omega as the Fourier transform, the answer will become V1 omega multiplied by V2 omega. Okay, as simple as that. We shouldn't have to do the convolution, but you can just multiply the Fourier transform for V1 and also for V2. Okay, given the example 7 here, with two signals f1 and f2, which is the exponent function multiplied by ut, and this one also another exponent function, and a and b constant here, both are bigger than 0. So for the solution, if you want to find the ft, which is the convolution between f1 and f2t, okay, instead of doing convolution, which is quite complex, what we can do is we perform the Fourier transform and we just multiply f1 omega and f2 omega. You need to find the Fourier transform for f1 first. Okay, so based on the table, based on the given list of formulas, we'll get the Fourier transform for f1 is 1 divided by a plus d omega, and for f2 is this one. So you just multiply this, okay, solve this equation, we will get this equation. And from this, if you want to find the ft, the original signal, you can just perform the inverse Fourier transform for this f omega, and it will become like this. Okay, so I'm not going to show you one by one how you obtain from here to here and here. This is just a mathematics, and from here to here you can refer to the inverse Fourier transform. All right. Okay, and the next properties is differentiation. So we are going to finish all the properties in this video lesson first. Okay, so for the differentiation, if there is a differentiation with n here, differentiation with n here, for the Fourier transform, it's just that it's just j omega with the power of n here and multiply back by v omega. Okay, let's say example 8, given gt as a triangle function a tri t with the amplitude a, okay, and the differentiation for this gt, okay, we will get this rectangular function, and if we further differentiate to the second level, we will get this pulse function. Okay, so how do we obtain this? Okay, first, okay, we know that if we solve mathematically in time domain, okay, we want to find the differentiation of this triangular function between 1, 0 and 0, 1. Okay, we will get differentiation of this. We will get this value, okay, a, okay, which is actually a rectangular t plus 0.5. And for this is negative a rectangular t minus 0.5. Okay, and for second order differentiation, okay, for this rectangular function, we will get this impulse function. Okay, so this is given as a delta t plus 1 minus 2a delta t plus a delta t minus 1. Right. Okay, so when we want to find the differentiation of the first time domain bt, okay, and we want to find the Fourier transform for this differentiation, this one is actually Fourier transform of a rectangular t plus 0.5 minus a rectangular t negative 0.5. So from here we know that we can use the sinc function, okay, sinc function which we obtain from the list of formulas. Okay, so this is a sinc omega over 2 exponent j omega divided by 2 minus here this part. Okay, however, for this Fourier transform, you need to multiply by j omega. Okay, refer back to the equation or to the formula here. Okay, for the first order, this n should be only 1. Okay, you multiply by v omega, and in this case, v omega here is given as this, okay, a sinc. Alright, so g omega here is actually this function here divided by j omega back. Okay, so you rearrange here, you solve for this, okay, so that it will become in terms of sinc function, you'll get a sinc squared omega over 2. Okay, so if we refer back here, okay, if you want to find the g omega for the triangle, okay, if we look straight at the table, we will also obtain the Fourier transform for that is a sinc squared omega over 2. Okay, and this is another example for second order differentiation. Okay, for this second order, we perform the Fourier transform for the impulse function that we have obtained the equation before, and for this j omega here should be squared. Okay, multiplied by g omega, which is the original one that we have obtained before. Okay, this is also equivalent to a exponent j omega minus 2 omega plus a exponent j omega. Okay, so g squared is actually negative. Okay, so you solve for this. Again, we solve for this, and also we put j omega here, divide this part of equation, divide by omega squared, we will get a sinc squared omega over 2. Okay, so how do we obtain from here to here? This is by using the trigonometry series. Okay, so when we plot g omega, we will get like this. Okay, which is the async squared function. Okay, basically this example wants to show you how do you want to obtain the Fourier transform, okay, for this original function, which is gt, using differentiation. Okay, using differentiation, and also using the property for first order differentiation and also second order differentiation. Okay, so to make more sense for all these properties, I will show you more examples in the tutorial video lesson that you should watch on Thursday. So until the next video lesson, thank you very much.